All right, in the 7.3 notes, we're going to be looking at things called electron configurations, which are basically like address of where the electrons are located. It can be a little bit um, different at first, and you just need to be patient and give yourself a little time to get it down. But it's very foreign, a lot of these terms, and because we can't see any of this stuff, it becomes a little abstract sometimes. So the history of the atom timeline, just very briefly, we know we had just a sphere really until like the 1800s, when John Dalton finally was able to do some experiments to prove some of the qualities of an atom, but he didn't know about anything inside the atom. So Thomson in the late 19th century, he did some experiments that led to the discovery of the electron, but we still didn't know about the nucleus. The nucleus was Rutherford in not that long after that. Um, and then the electrons were then like, okay, they're zooming around. These are pieces of plum, just like spread out. Now they're like, okay, they're going around the nucleus. And then Bohr did more experiments to realize, no, it's not quite that easy. Electrons can be found in what are called energy levels. So they're quantified. And then our most recent and sophisticated model is the modern quantum model with the electron cloud. And the electrons, they're very, very small, and they're always moving, and they are not, going around in these fixed orbits. So they're actually determined by probability. All right, so we're going to look at the electron cloud and how it's organized. So electrons are in constant motion. It's hard to know where they are in the cloud. This is called the quantum theory, which is the mathematical description of wave properties of electrons and other tiny particles to estimate where they are probably. An orbital is a three-dimensional region around the nucleus that shows where an electron it probably is. Okay, we have what are called shells or energy levels. Okay, this is kind of like our top of our hierarchy. I use usually energy level terminology. Shells, sometimes though, you might see. We number these shells or energy levels like 1, 2, 3, etc. 1 is the closest to the nucleus, and then as we get further and further from the nucleus, the numbers go up. Each shell holds a maximum number of electrons. Each shell has what are called sublevels, which are lettered S, P, D, and F. And by the way, the S, P, D, and F also refers to the shape of orbitals. And an easy way to remember is S is a sphere, P is a peanut, D is donut, and F is flower. So they can get quite complex as they go from S to F. S orbital only holds up to 2 electrons, P is going to hold up to 6, D is going to be 10, and F is going to be 14. So our subshells, first shell will hold 2 electrons total. We have 1 orbital, which is the S orbital. The second shell has 8 electrons total because it has 2 orbitals. It has S and P. And then third energy level holds 18 electrons total. It has 3 orbitals, S, P, D, and F. And this is S has 2, P has 6, and D has 10. Again, I know all this seems very weird, but it all comes together. So we'll take notes on this first, and then we'll practice and see how the periodic table figures in to all this. All right, electron configurations is the most stable arrangement of electrons in an atom's electron cloud. It's a shorthand notation for tracking the electrons in an atom, and it represents the quantum mechanical model, which is more accurate than the Bohr model. Electrons can act like waves and particles, and thus we use quantum theory to predict how they are arranged. So there are 3 rules to determine the electron configuration of an atom. We do not need to know the names of these. So if you see Hund's rule, Pauli exclusion, or Aufbau principle, we're just really applying them, but we don't actually need to know the names. So Electrons always fill the lowest energy orbital first. That's number one rule. Therefore, it's going to fill closest to the nucleus. And orbitals of equal energy, you're going to get one electron before any orbital gets a second pair. So when we do orbital diagrams, we'll draw that. But when we're doing configurations, it's kind of hard to show that. And think about it, electrons, if they have more spaces to be, they're not going to pair up in the same orbital, which is the same space, because they're going to have a lot of electron-electron repulsion. No two electrons in the same atom can have the same set of quantum numbers. Quantum numbers we're not really looking at, but they're saying is all electrons are unique as far as where they're located and all the different characteristics about them. They can be spinning, or they are spinning, but if they are in the same orbital, they're going to spin in opposite directions. So one will spin clockwise, the other one spins counterclockwise. All right, grab your electron configuration table. I gave this to you at the very beginning of the unit. So if you don't have that with you, pause, locate it, and then also get 4 different colored pencils. All right, so we're going to shade this so it's easiest to interpret as far as how to read configurations. Let's go ahead and color 1A and 2A plus helium, the same color. So groups 1A, 2A plus helium. If you want to follow these colors, that's fine. If not, just color them all the same and key them out. Then you're going to do that for P. P is this block over here. So go ahead and just model this. D is going to be the middle block, the transition block. And then F is going to be the bottom, the inner transition metals, or lanthanoids, actinoids. All right, in addition, let's label this. I would not necessarily label or draw the arrow because I think it's going to get really messy, but I would, write 1s or to the left of hydrogen. This is 2s, 3s, 4s, 5, 6, and 7. And then you have 2p, 3p, 4p, 5p, 6p, and 7p. So however you need to label this in order to understand it and still be able to read the table. All right, in the middle, 3D actually is in the 4th row. Let's talk about that later, but we'll go ahead and label this 3D, 4D, 5D, and 6D. And then on the bottom, 4F and 5F. All right, this is also just another reference to help you remember the order that it fills. This is on your reference, so if this is helpful, use it. I usually just use the flow of the table. I think that's sufficient, but 1s, 2s, 2p, 3s, 3p, 4s. Every time you go over to the right and you're repeating that diagonal, how it's being filled. Okay, electron configurations, how to write them. So first of all, we're going to number the shell or energy level. So 1, 2, 3, whatever it is, the letter of the orbital, S, P, D, or F, and then the number of electrons in that orbital. Okay, and you will just do that until you run out of electrons. So for example, hydrogen. All right, well, hydrogen is the first element. So you're going to say 1s, because you're in the 1s, and you're at position 1. So 1s1. And the last one, is going to be a superscript. All right, so 1s1 is the configuration for hydrogen. This is the shell or energy level, that first number. The letter is the letter of the orbital. And then the superscript 1 is the number of electrons. All right, helium is right next to hydrogen. So helium, you're in the 1s, but not at 1, but 1s, 2. All right, again, that's the anatomy of it. And then we'll try a couple other ones, lithium and nitrogen. For lithium, okay, is right here. We're going to always start back at the top here because everything is going to fill from lowest energy level first. So we're going to fill this completely. This is 1s2. And then follow the flow of the table. We're going to hop down here. We're at 2s at position 1. So our complete configuration is going to be 1s2, 2s1. And then we have nitrogen. Let's try that one. For nitrogen, which is right here, again, we'll start at the top here. So we're going to fill this completely, 1s2. We're also going to fill this completely, this energy, or this orbital, 2s2. Now we're still in the same energy level, but now we're hitting a different orbital in sublevel. So we're now at 2p1, 2, 3. So we would say 1s2, 2s2, 2p3. Okay. And if you were to add up these superscripts, as 2 plus 2 plus 3 is 7, you're at atomic number 7, 7 electrons total. All right, so here's some practice. We can do maybe one of the ones down further. So I'm going to look at nickel. Now for nickel, that is right here. Okay, so just follow the labels here. We filled this completely at 1s2. Then we're going to fill this at 2s2. Follow the flow of the table. We're going to fill all of this. So there's 6 elements here, so 2p6. Keep going, 3s2. Keep going, 3p6. Hop down here, 4s2. Now this becomes 3D, remember, and we're not filling it completely because we're at position 1, 2, 3, 4, 5, 6, 7, 8. So 3d8. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. All right, if you didn't quite get that, it will show up in a moment. But try the other ones, pause this, and then check the answer key. So you can see how long this gets. And of course, there's a shorthand way, but we have to know how to do the long version first in order to know how to do the abbreviated way. So just a couple other things. What happens from period 4 on, remember that it kind of goes out of order here. Instead of after 4s is 4d, it's 3d. So the reason for that is the 4s sublevel has slightly lower energy than 3d. Again, a little bit more complex and advanced. So if you could just accept that, or you can do more research on it if you like, or wait till you get to AP if that's something you're interested in. Transition elements transition because their s and d orbitals are so close in energy that electrons can be lost from both. So sometimes zinc can lose 1 electron to be stable, and sometimes it loses 2. So it becomes a little bit unpredictable as far as when we get to the transition elements. All right, noble gas notation is our shorthand way. So the abbreviated way to write electron configurations. And so instead of writing all that notation out, we get to write just a little bit of it and use the noble gas that is prior to whatever element we're talking about. We get to put that in brackets and then just finish whatever remaining notation we have. So for example, calcium. So if you look at calcium, it is right here, number 20. All right, so instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, what we would do for this is we would go backwards. We always have to go backwards to the previous or prior noble gas. In this case, it would be argon. And we would write AR, its symbol, and then we would put it in brackets. Again, this is just the way they do it. So argon in brackets, and then you would say 4s2. So argon's, it means like argon's configuration plus that. All right, let's try one of these. Since we did nickel already, we can try that one. And then these are the same ones that you had to practice last time. You just have to now put them in a shorthand way. So nickel again is right here. So go backwards. So it's argon as well. So you would write AR in brackets, and then you would write 4s2, 3d8. All right, because these two we haven't done yet, go ahead and pause this, try these out, and then go ahead and check your answers. All right, try these out, practice electron configurations, and be patient because it is a very abstract kind of thing at first, but it will be, hopefully, it will get more clear as you give it a little time.